Hey guys, welcome to the second video on Syn and Addition. This one is going to be going over what alkene reactions you guys have learned that are syn and anti. Alright, so let's get started. So in the previous video, you guys saw that I said H2 PDC, right? H2 over PDC was a Syn addition, right? So yeah, so that is one reaction you guys have learned that's a Syn addition. Another reaction that you guys have learned that is also a Syn addition is actually hydroboration, right? So remember having an alkene like this, right? And then if I put step 1, BH3, THF, and then step 2 would be just H2O with NaOH, right? That is also a Syn addition, and so and if you remember that BH3 adds an alcohol group to the least substituted carbon of the double bond, right? Remember when you guys were studying, that was a kind of a bad example. Here, let's write it like this now. When you guys were studying for exam 1, the answer to that question would have simply just been like this, right? And a hydrogen would have been added to the most substituted, but now because it's stereochemistry, that doesn't cut it. And so Syn addition could have either added the OH and H like this. And remember, because the H here is wedged, it would make that methyl dashed plus we could do it if the OH was and H are added dashed. And then that methyl would be wedged. Okay? And so that is an example of Syn addition with hydroboration. Alright? And so those are the only two reactions that are Syn that you guys have learned. Okay? So now we can move on to anti-addition. So anti-addition are going to be any of the reactions that involve a 3-member ring intermediate that you guys have learned. So like using something like this. That was bad. Right, so I draw it like that. And then something such as Br2, right? Or Br2 over ROH, where R is an alkyl group, or another hydrogen to give H2O, water, right? So that covers the bromination, the halohydrogen formation reaction, right? And so those are going to be anti-additions, okay? So yeah, either just the two halogens by themselves, that should really actually make this written like this, X2, X2. So X could be bromine, chlorine, iodine, not fluorine, okay? And also, if you guys remember that HBr with radicals, so I'm going to write that as ROR because there could be those two R groups don't necessarily have to be H's to give you H2O2. So HBr with radicals, I just want to make it clear right now, that is not a Syn or anti-addition. There is no Syn or anti-addition for that. Okay, so just wanted to say that now. Now, one other thing I want to mention is that any reactions that have a carbocation intermediate, those are not Syn or anti. Okay, those do not use Syn or anti-addition. All right, and so why exactly is that? Like why exactly would it be that a carbocation reaction will not undergo Syn or anti-addition. So let's actually use an example. So we can have something like this, and a double bond there. Okay, let me just make that a little bigger. All right, and so let's say the reaction is going to be H3O plus over H2O, so an acid catalyzed hydration. So if you guys remember the mechanism, we're gonna the double bond grabs a proton, so I'm gonna just draw it coming from H3O plus. Okay, and so double bond grabs the proton, and that bond breaks to go to the O. So we're going to form a carbocation, right? The hydrogen added here. Oh, you know, that was also another bad example here. How about let's erase that bond. Like this. And so the hydrogen would have added here. We would have formed the carbocation on the secondary carbon because it's more stable, right? So now we're faced with a situation of either having the H2O attack the carbocation, the secondary carbocation, or we could do a shift, right? So we have a hydrogen over here, and so that can shift right there. Okay, and so what would that look like? So now we have, and I'm going to leave off the red hydrogen. We form a tertiary carbocation there, right? So notice what happened. The carbon with the wedged methyl, right, the tetrahedral carbon, sp3, becomes, it's going to be now sp2 because it lost a hydrogen atom, so it only has 3 things bound to it, and becomes planar when it becomes a carbocation. Why does this happen? Remember, a tetrahedral carbon or an sp3 carbon is a requirement to be chiral. Okay, this carbon, 2 planar bonds, a wedge bond, and a dashed. That's a tetrahedral carbon. A sp2 carbon is now going to be called trigonal planar. 3 planar bonds. All right, they're all kind of flat. And so it loses any stereochemistry it has the moment it becomes a carbocation. And that is true for all atoms, for all carbon atoms. Anytime you have a carbocation that ends up on a carbon that used to have some sort of stereochemistry, it instantly loses all stereochemistry. And it will become planar. Okay? And so now what can happen? Remember, we still have our H2O, and so it can attack in 2 ways. It can attack from the back, right? From the back, it would make the methyl a wedge, and the H2O added dashed, and it would obviously get deprotonated, right? We have, just say, another H2O come in, grab this, and so it would look like this. Right? Or it could have attacked from the front. And so in the end we would have something like this. I'm just going to skip the mechanism. And it becomes wedged. Okay? Now, what's more likely for it to be attacking from the front or back on a carbocation? They're all equally likely, so you again get a mixture. Now, in this case, if you actually look This is not a chiral carbon, but everything I've still said is true in that carbocation loses its, a carbon that used to have some sort of stereochemistry loses its stereochemistry the moment it becomes a carbocation. That is all still true. And so that is a very important concept to keep in mind. So any of those reactions that you learned with carbocations, be extremely careful with them, because on a test what they could do is they can give you some sort of compound with stereochemistry, right? You can even do the RNS and you'll see that it has stereochemistry. And then they'll have it react with some sort of carbocation forming reaction. And chances are the carbocation will end up on the carbon with the stereochemistry. Now, obviously, they don't always have to do it, but they can. And in that scenario, you have to know that any stereochemistry is lost, and that the group that attacks the carbocation can attack from the front or back. So you can get it to be either wedged or dashed, and that will then influence if we have something like an enantiomer, right, or some enantiomer mixtures or some other sort of compound, right? So always just keep that in the back of your head, all right? And so I hope this video helped. In the next one, I'm going to be going over specifically Syn Addition with H2PDC. There's a lot of ways that they can throw you guys off with that, mainly dealing with bond rotations. And so I want to help clear that up in the next video. So if something here didn't make sense, please feel free to email me, talk to a TA. Or if you're watching this on YouTube, please feel free to comment your question below so that others who chances are have a similar question or the exact same one to yours will be able to see the answer as well. All right. And so I will see you guys in the next video. Good luck.